Okay, so now moving on with the next step of our simulation. We were done with the mesh previously, and now we go to the setup. Just click Edit, and the Fluent window should pop up. I've already waited for the model to load. It takes a few minutes because the mesh is very big. So to start, I'm just gonna put my gravity here, and you should check your units if you wish to. I'm already satisfied with the units that I have. Um, Pressure based, steady, could be either steady or transient depending on the angle of attack that we are checking. Since we're starting with a very low angle of attack, the steady simulation will do just fine. So as for our viscous model, we will be using K omega SST. This is a good model when you're looking at calculating forces around the wing. Materials, if you wish, you should check the properties of the fluid. It's all right. Boundary conditions. We are going to edit the inlet. We have a velocity type of boundary condition, and here I'm just going to change it to magnitude and direction. Uh, I'm going to give it a 33.62 meter per second velocity magnitude, and these vectors um, just dictate the flow components. Uh, I'm gonna leave I'm gonna leave it as is right now, but if you are trying to uh, get the results for different angles of attack, this is where you do it. You change the X component to something like that, and the Z component to something like that, for example. You can get those by calculating the sine and cosine angle of the angle of attack. So for example, if you're looking at, let's say, angle of attack of 4 degrees, you calculate the cosine of 4, but whatever the value is here. And then for the Z component, you just use the sine of 4. Here, I'm just going to change this to 1% turbulent intensity in the inlet, which is it's a reasonable amount. Um, I already know that the outlet is okay, but if you want, you can check that. Gauge pressure of 0 in the outlet, and reference values. I'm not going to change anything here, but if you can give it a reference area equal to the reference area of the wing, so that you can calculate the coefficients directly. Since we're calculating the loads, it doesn't really matter which area we have. As for methods, I always like to use coupled, and I don't change anything here. I just change this to second order, and this one also to second order. Mm, Report definitions. I'm gonna create a force report for drag, but I'm gonna call it FX instead of drag, because later on you'll see that the forces are defined in the body axis, in the body coordinates of the wing. Not necessarily they mean drag, you know. Um, like when you're looking at higher angles of attack, or just different angles of attack from different from 0. That's what I mean. The forces are still going to be defined in X, Z, and Y, or X and Z for our case. And if you have, for example, an angle of attack that is like this, like the fluid is coming in this direction, you're having forces, Fx and Fz, and then you gotta decompose those forces in the actual drag and lift by applying a coordinate transformation um, from the body coordinates from the body system to the wind system. But that's a conversation for another video. But for now, let's call it what it is. Let's call it Fx. I'm gonna choose drag force wall. The vector is 100, and I could choose report plot, but I'm not going to now because we're gonna run the simulation as a batch process, so there's no graphic user interface to actually see the plot. And yeah, this is it. As for lift, I'm gonna call it FZ. It's gonna be a lift force wall. It's not Y, but it's defined at the Z axis. And same thing. Um, okay. And I'm gonna create a moment. Moment wall. The moment center. I don't remember exactly what it was, but I'm just gonna give it a value here of 282. I think that was it. This is the moment setter location, at least the one that I expect to be. And the moment axis is not Z, it's Y, because we're looking at pitching moment, therefore around Y. And okay, so now for the monitors, we want to establish a convergence, well, convergence criteria to the simulation, uh, just to avoid a very long time of calculation run. So what I like to do, uh, I don't, I'm not gonna plot it because once again we don't have the GUI for the batch simulation. I'm gonna change these to, I'm gonna add of mag of um, 2 orders of accuracy to all of the residuals except for continuity. I do that because I found that it's very hard to get uh, a 10 to the minus 5 order of accuracy for continuity alone. I'm not sure why, but uh, doing some research, in forums, Ansys forum and Google, somebody mentioned, one of the staff mentioned that if you have like 10 to the minus 3 continuity residual and you have convergence in the variables that you're looking at, uh, that's a reasonable convergence criterion. But of course, you can, if you want to increase the order of accuracy for that residual, it's up to you. So uh, I print it to console so I can keep track of it while the simulation is running, and hit OK. And now I'm gonna add a convergence condition, another one. For that, I create one for fx, and 10 to the minus 3 is a good amount. I'm going to ignore the 21st iterations, and I'm going to use, let's say, 10 iterations and the convergence for this particular variable. I'm also going to do the same thing for fz. And the same thing for the moment. And here we have all, well, yeah, all conditions should be met, and okay. I'm not going to work with cell registers now. And I got to initialize my simulation. But this is going to take a little, like a few minutes. So I'm going to stop recording and come back once it's done. Okay, so now that the solution is initialization is completed, I'm able to come here to calculation activities, and then I'm going to, no, not this one, sorry. I'm going to edit um, the data file quantities that I actually want to be generated from the simulation. So there are the standard quantities, but I found that like some of these, I mean, I don't have all the quantities that I need for my analysis, so I'm gonna select some additional ones from this list. Um, I'm going to add turbulent intensity, turbulent kinetic energy, the turbulent viscosity, and Y plus. What else? I'm gonna add the wall shear stress as well. And I think that's it. Yes. Yep, this is it. Hit OK and OK. And now for the run calculation. Um, I'm going to put 500 iterations here, but it's up to you. You can put however many iterations you judge is necessary. And I'm not gonna hit calculate because this is my personal computer. What I'm gonna do for now is just I'm gonna check the mesh, and it's gonna take a little bit. Since it's a very big domain, it sometimes it can take a couple of minutes to get that done. And now we're just gonna evaluate the mesh quality. Okay, done. After those, you're done with those, you can just check the case. And if you get this window, it's perfect. It's amazing. Sometimes you can get some recommendations and then you can go back to meshing and change your mesh, but not at this point. So instead of hitting calculate, I'm just gonna uh, export the case, and I'm gonna use the standard folder, the standard path. I'm just gonna change the name of the case to test. Let's say test sim AOA 0, test simulation angle of attack 0, and hit OK. So it's gonna take maybe a couple of minutes to write the case file. I'm gonna pause this recording and then get back later. Okay, so after exporting the case file to the standard folder, all you gotta do is close the Fluent window and you'll be back to the workbench, excuse me, the workbench window. Uh, and that concludes the setup. And I will just finish the video with showing you guys how to find the actual case file, because that's going to be important in case you're using a high performance computing center to run your simulations. most people don't really have a computer that is powerful enough to run the simulation of this sort with such a big mesh, and they rely on high performance computing capabilities to run the case. And so the way you find, let me, you go to the folder that you created um, previously, like before, even before setting up this whole thing. You had a folder. In my case, it's called test simulation, where the workbench um, where the workbench thing is going to be saved. And the way you find the case file that you would just exported is just you go to this one that is created automatically. Go to DP0 FLTG Fluent, and you're gonna find your case file right there. Uh, Thanks for watching, and the next step in this video series will be to actually use high performance computing to run and obtain data from your simulations. Thank you.